Okay, so here we have an example of how to transfer linear momentum into angular momentum using a reference point. In this case, the reference point is going to be our axis of rotation in the schematic here. So you want to take a second, read the problem. This way you can understand the work that I want to set up for you here. Okay. All right, other than that, let's get started. So the diagram shows there's a bullet moving to the right, and then it's going to strike this metallic box, which is welded at the end of this disc. So therefore, the whole entire system is going to rotate after the collision. So the first thing you got to recognize is that you can transfer or connect linear momentum into angular momentum simply by taking this particular vector here, which is the velocity vector, multiply that by m, which would give us our linear momentum. And then to transfer linear momentum into angular momentum, we just need a reference point. In this case, the reference point is at the center of the disk, and that distance to the box there is the distance of r, which is already perpendicular to the direction of the bullet. Okay, so we have this function here. The initial angular momentum is CRP, where C is the coefficient, aka in this case, it is a point mass, so it's going to be 1. R here is defined as the distance from where the bullet is going to strike the box to where the axis of rotation is. And that in this case is the distance of actual R, which is given as 0.5. And then P here is just the linear momentum. All right, so let's go ahead and expand this function down into P. We can expand that into the mass of the bullet times the velocity of the bullet. And other than that, we can rearrange it where I just pulled out the mass of the bullet in the front because ultimately you want to cross R with V. Again, you need perpendicular stuff for angular momentum. So I just kind of drew a dashed line here that goes through the axis of rotation, and then which is parallel to the direction of motion of the bullet. But then you need an R that's perpendicular. So in this case, the radius of the disk is already perpendicular to the direction of motion. So we don't have to do anything fancy here. All we have to do really is just plug and chug. Okay. So the coefficient for a bullet or a point mass in this case is just a 1. The radius which is given as 0.5 the disk, and that is the distance from where the bullet strikes the block to where the axis of rotation is. And then the mass of the bullet is given as 10 grams in the wording up here. I went ahead and convert 10 grams into kilograms. So make sure you pay attention to units. You do need to convert 10 grams into kilograms, and that is going to be 0.01 kilogram. And then the speed of the bullet, or the velocity of the bullet in this case, is directed to the right, which is given in the schematic as 600 meters per second. So part A is pretty straightforward. It's just a lot of plug and chug. Okay. If you do your calculator work, you should get 3 kilometers meters square per second. And since they asked for the magnitude, we'll just stop there. All right, let's move on to part B. So part B asks for the angular speed immediately after the bullet it's embedded in the metallic box here. So first, we have to set up conservation of momentum. In this case, linear momentum can be translated into angular momentum simply by taking P cross R, which we'll do here. So the initial angular momentum we just calculated in the previous problem, which is 3. And then now we can set the initial equal to the final angular momentum of the system. In this case, you notice here the moment of inertia is I total because we have the disk rotating, we also have the box rotating, but then now we also have the bullet, which is stuck inside the box. So the box and the bullet in this case can be treated as a point mass since the problem says that the width of the box is much less than the radius of the disk, implying that you can treat it as a point mass. All right, so we can go ahead and expand I total into 3 terms. There's the moment of inertia for the disk, the moment of inertia for the box, and then the moment of inertia for the bullet. And then that will be times omega f here, which is what you're trying to find. All right, so let's expand I disk, the moment of inertia for disk. Hopefully you know by now it's 1 half m disk r square, r being the radius of the disk, because the axis of rotation here is right through the center of the disk. So nothing funky here. All right, the I value for the box is simply mr square. Again, the coefficient is 1 because we assume the box is so small that we can just treat it as a point mass. And then the r here is r squared, r being the distance from where the box is, which is on the edge of the disk to the axis of rotation. And then the mass of the bullet as well, which is inside the box. So really here we have 2 terms that are pretty similar. Okay. All right, we can go ahead and plug in all the values. Mass of the disk is 4. I left the units out just to keep it clean. and then the radius of this is zero point 0.5. We'll square that. The mass of the box is zero point 0.5 given in the schematic. The radius here, the distance from where the object is to where the axis rotation is the distance of r as well, which is 0.5 square. And then the mass of the bullet, once again, it's in kilogram here, 0.01 kilogram. And then that is also a distance of zero point 0.5 square because it is stuck to the box, which is on the outer edge relative to the axis of rotation. So in this statement, the only thing we have unknown is our omega. So if you punch in all your calculator work, you should get the summation here at 0.6275. And then all that's equal to 3 because we already found omega, angular, the initial angular momentum in part A. So Li, which is 3. So I went ahead and substitute in that number there for Li. And then really in this last line, the only thing unknown is our omega F. So the final omega F, we divide both sides by 0.6275. And if you do that on your calculator, you should get approximately 4.8, which is your answer here. And so the answer is 4.8 rats per second. And since it asks for speed, I'm not going to tell you if it's clockwise or counterclockwise because that's unnecessary. Okay. All right, that takes care of part B. And then let's go ahead and move on to the last part C. Part C is pretty straightforward. It's looking for the amount of energy lost during the collision. So this is an inelastic collision where the bullet is going to exert some of that energy and transfer into like thermal and friction and stuff like that inside this box. So to do a mechanical energy loss, we have to figure out what the initial is and what the final is. And the initial kinetic energy simply just comes from the bullet because it is the only thing that was moving initially. The problem states that the disk was initially at rest, therefore the box is also initially at rest. So we plug in stuff we know. The function for it is 1 half m v squared. In this case, is the mass of the bullet, and the mass of the bullet is 0.01. It is initially moving at a speed of 600, and we'll square that. All that calculator work is going to yield 1800 joules. So that's your initial kinetic energy. But then now we got to find the final kinetic energy. So the final kinetic energy here is simply just due to rotation because the system is fixed to an axle. So therefore it's just spinning. It is not moving linearly. So all we have to do is use the same format. 1 half, except for m, we'll do the moment inertia of the system, and we'll square the final speed there that we just found in part B. So if we expand again, I total to include all three items, the disk, the box, and the bullet, and then omega F, and we got to square that because that is the function. And then once you plug in all the values, mass of the disk is 4, the radius of this is 0.5 square, mass of the box again from the diagram is 0.5, the radius of this is 0.5 as well, or the distance where the box is 0.5 meters away from the axis of rotation. The mass of the bullet here is 0.01, and it is also a distance of 0.5 away from the axis of rotation. And then 4.8 comes from our previous answer for the final angular speed, which is 4.8, and we'll square that. And we punch it all in the calculator, we should get about 7.23 joules. Now, to find the mechanical energy loss, all we have to do is take the kinetic energy final minus the initial, which in this case will be 7.23 minus the initial of 1800 joules, which we found up here. And that's going to yield us a negative 1792.77 joules. Okay, I hope that helps. All right, other than that, stay nerdy and don't be whack.